In this section, we're going to be studying both the wave and particle nature of light, energy, and then we'll take it eventually to the next level and even talk about the wave nature of some macroscopic objects like baseballs and cars. So we need to have a working definition of some of the common terminology surrounding waves. So first, let's come up with a definition of a wave. So a wave is a disturbance that travels through a material. Oftentimes when you look up the definition of a wave, they talk about the disturbance traveling through some kind of medium. And that can be kind of confusing if you've never heard of the word medium before in that context. So a medium is just a material, and even a vacuum, electromagnetic radiation, which we're going to discuss on the next page, travels through a vacuum at a specific velocity, the speed of light. So even the absence of all material. So in a vacuum, there's nothing there. Everything's been sucked out. Air, there's no molecules in there. Even the vacuum is considered a medium because electromagnetic radiation can travel through the vacuum. So very all-encompassing kind of idea, this material. It could be water, it could be air, it could be a solid. The disturbance can be a multitude of things as well. The disturbance can be energy. The disturbance can be light, which is a specific form of energy. It can be sound. It could be motion. So, which again, the motion is actually another form of energy. So there's lots of disturbances that we can imagine traveling through whatever, because honestly the material or the medium is a whatever situation. It's traveling through something. The next definition is for amplitude. Amplitude is the height of the wave. When you're listening to the radio or something like that and you turn up the volume, you're actually manipulating the amplitude of the wave. So the units there, we're talking about height, so the units are going to be some kind of units of length. So meters would be our base unit. To be perfectly honest though, it gets super small. So a lot of times you'll see nanometers or picometers as your units of length. Centimeters. It could be all over the place. Depends on what kind of wave. How are we going to measure this amplitude? So we're going to start at the equilibrium position. Which is the position that the wave would settle into if it wasn't transmitting that disturbance. So imagine this wave being like a guitar string, right? And so if no one's playing the guitar, then we would expect the string to be perfectly straight there. And that's what we're going to call the equilibrium position. So in order to measure the amplitude, you start at your equilibrium position and you go to either a high point, and these high points are known as crests, or you start at the equilibrium position and you go to the lowest point, which is known as a trough. Wavelength is the distance between two successive crests. What that means is we start at the first high point and we measure the distance to the second high point. So from one high point to the next high point. Or we could look at the low points and also get a wavelength. So we look at the first trough and then we measure the distance to the next trough, the next low point. I keep on emphasizing we're measuring the distance. So again, we're looking at something that has units of length. So our base unit would be meters. The symbol here is important because we do see wavelength in a lot of our calculations. So the symbol is going to be the Greek letter lambda. personally, I think frequency is the hardest of the terms on this page. So I want to give you an analogy, a story to help you understand what frequency actually is. So say I asked you to calculate how many cars pass by your house on a Saturday morning. And so you might set up a chair, I don't know, on your porch or in your front yard or, I don't know, wherever, by the street. And we have the street that's in front of your house. And so it's a bumpy street. They haven't paved it in a while. And then we need a point is what it comes down to. So we can't decide, okay, do we count this car? Do we not count this car? I mean, what happens if your neighbor comes home and they drive to this point and then they turn into their driveway? Are you going to count the neighbor as passing by the house or not count the neighbor? So you're going to pick a point. So maybe it's a tree across the street. And you're like, I'm not going to count the cars until they pass by the tree. So that gets rid of some issues of who not to count and who to count, right? We're only going to count the cars that pass through this given point, which is the tree across the street. So you come back to me and you report your data, and I'm like, I need sig figs and units. No, forget about the sig figs. We need units though. So what kind of units would you give me? You might tell me, well, I had 3 cars pass by that tree in 1 hour. So you might say cars per hour. So that's if you live on like a remote street, right, in the middle of nowhere. 3 cars per hour isn't that much. But say you live on a super, super busy street, and I don't know how you get this value, but you're like 10 cars pass by that tree every second. So you have some kind of counter and you're counting fast because you live next to the freeway. I don't know. So what are we counting? We're counting the number of times the cars pass by that point. And it doesn't have to be a tree. It could have been a mailbox or a rock or something. But that point is really important in terms of our definition. So when we're looking at frequency, we're calculating how many times the wave passes through a given point. So we can think of it as the crest of the wave passing by a given point. The numerator, what actually are we counting on the wave, gets pretty iffy. So let me write like 10 crests, and then whereas the crests are analogous to the cars, and then we're like per second. But I don't know, that sounds kind of wonky, right? So instead, we're going to leave out the unit in the numerator, and we're just going to say 10 something per second. So our units become 1/seconds. Officially, the definition of frequency is the number of times that a wave passes through a given point. Let me write that down. Or mix it up a little bit. The number of waves that pass through a given point. When we say given, we mean like defined. We defined it ahead of time. Point per unit time. The units for frequency are officially 1/seconds. However, we don't necessarily always write it like that. You can write it as hertz, which is abbreviated capital H, lowercase z. And that's the same thing as writing 1/seconds. The symbol for frequency looks like a fancy letter V, but it's actually the Greek letter nu. And we'll be using that as our symbol for frequency. So the purpose of this picture right here is to illustrate the relationship between wavelength and frequency. First question for you all. Which of these two waves has a greater frequency? So if you selected the top wave, you're correct. This has a greater frequency because it goes up and down quite a bit more in the same distance compared to this bottom wave. This bottom wave seems kind of slow, right? It's just taking its time going up and down. So that means that this has a lower frequency. But let's look at the wavelengths, and they notated them as lambda. So we have the wavelength on the top, which is pretty small compared to the wavelength on the bottom. So wavelength and frequency have an inverse relationship. We can say as frequency increases, wavelength decreases. And the opposite also holds true. We can say as wavelength increases, we would expect frequency to decrease. So electromagnetic radiation is actually two waves. So first we have the electric field, which exists as a wave. And that wave is going to be perpendicular to a second wave. And the second wave is for a magnetic field. So just to illustrate what I'm talking about a little bit more here, you have your electric field, which is moving across the plane of the paper. So I'm highlighting that in yellow. And then 90 degrees from that, and we can think of it as going into the plane of the paper, we have this magnetic field, which is also a wave. So we have these two waves, and you'll notice I drew both waves in the same direction, like I colored them going from left to right. So the direction of travel goes on the third perpendicular axis. So that direction of travel is perpendicular to both the electric and magnetic waves. This is where we get ideas like the right-hand rule if you've taken a physics class. The cool thing about the electromagnetic radiation is it has a constant velocity in a vacuum. So we're going to define that as letter c, which is the speed of light, and it's 2.99 times 10 to the 8th meters per second. If need be, if you need more sig figs for whatever reason, you can Google the speed of light, and that value has a lot more sig figs. But for most of my problems, I'll use 2.99 times 10 to the 8th, or sometimes if I'm feeling lazy, I even just use 3 times 10 to the 8th meters per second, and it usually works out in the end. So the first equation that we're going to use this in deals with the fact that in a vacuum, the speed of light is equal to our wavelength times our frequency. In this box here on page 2, I would like to briefly go over some of the units, some new units that you might encounter in the quantum chemistry chapter. So the first one is a picometer, and we haven't seen that metric prefix thus far in our study. So pico is super, super small, and there's 1 times 10 to the 12 picometers in 1 meter. For this chapter, you're typically going to see it used as a metric prefix with meters, but of course you could have a picoliter or a picogram. those things do exist, but we mainly see it as a picometer. The next one, also for very, very small distances. Remember, we're studying electrons and atoms, so we need smaller units. Nanometer. I think we may have seen this one before. So 1 meter has 1 times 10 to the 9th nanometers. We also have something known as an angstrom. You might encounter that in one of your problems. So angstrom is symbolized by the Swedish letter A. So if you go to IKEA, you might see an A that looks like that. That reminds you of the angstrom. And an angstrom, well, there's 1 times 10 to the 9th, 10 to the 10th angstroms in 1 meter. So it's another unit of length, except instead of doing meters, they just do angstroms. And the fact that it's smaller than a meter and the fact that it's a unit of length is kind of all wrapped up in that symbol. And the last one, if I could just squeeze it on here, is the hertz. And it's important as we study, especially these first problems where we're studying frequency, that we automatically translate the hertz into 1/seconds. And that'll make the units cancel a little bit easier as we work through the material.